Okay, so welcome back to the second session of the interface analysis day. And so what we are going to do now is actually we're going to look into how to calculate a proximity histogram from what we did just earlier, and how we can generalize proximity histograms. And later on, we're gonna go and look into how can we make those local. Can I make a
Muted.
Yep.
Are you muted? Yeah.
So, oh, I'm muted. Sorry, I didn't realize I was muted. I I was just giving some. Okay, so welcome back to the welcome back to the second part of today, and the second part is going to be we're going to look into how to do proximity histograms, proxigrams from the objects we just created, and essentially from any object. It doesn't matter if you use the grain boundary model we just had, if you use a if you use a if you use an isosurface, or if you use point objects, if you use line objects, it will always be the same. So we'll go and look into ND analysis, how we can do ND analysis. Okay, and so let's get right into it. So how many of you already have a grain boundary? Did some of you manage maybe during the break to create a grain boundary? Okay, that's one green tick more than before. All right, at least some people were able to create a grain boundary. So what I've done is I've now also installed the screencast key. Sorry, I didn't have that before. So now if I do anything in Blender, you're going to be able to see what buttons I'm pressing, what I'm doing with the mouse, so that usually makes it much easier to follow. Sorry, I didn't have the screencast keys installed earlier. Okay. So we still have our data set loaded in. We've got our grain boundary as FV4. Yeah, that was the last patch that we've created. That's now our grain boundary, and we're gonna work with that. And the first thing we're going to do is just to create a proximity histogram. And we actually have a workflow for that, and you can see it's it's a relatively simple one, patch create proxygram, but we are actually going to go a little bit of more. Let's just start with that one. Let's just start with the simple proxygram workflow. So yeah, we've got our POS file, and you could choose a couple of different ones. Then we'll just choose the species. In our case, boron. The interface in our case is FV4, and the bin size, half a nanometer, is probably an okay. And then we can run the Proxygram calculation, and there you go, you have your proxygram. And you can see, we've got a nice concentration spike in the middle. But of course, I warned you already the day before yesterday that maybe concentrations at grain boundaries aren't the best measure of what's happening there. And actually, the grain boundary data that I've shown you during the field evaporation physics session was actually from that grain boundary. You can just click on the Proxygram workflow.
No, because Peter, normally you don't see on the left side the functions and the workflows. So for everybody to open a workflow, you can just type in open workflow, and then you hit the tab and autocomplete, and then you can select the desired one.
I am learning stuff. So open workflow. Oh yeah, that's actually pretty neat. I've never done it that way. Thanks, Martina.
You're welcome, and we also have all of the functions from the last session in a workflow, the workflow modeling grain boundary, if you missed a function.
Okay, that's pretty good. I didn't know that. No? Or I've never done it that way. But yeah, that's actually a pretty cool way to do it. Okay, so yeah, but so this is actually a quick way to do proximity histograms. By the way, if you do a proxygram for multiple species, you can also do multiple species. And if you create multiple proxygrams, then you can create multiple. Then you can copy the proxygrams from multiple axes. You can just click on a. Let me just reopen that again, and maybe. Yeah. So if I rerun the whole spiel here. So let's go and create one for boron FV4 and undock that and create one for, I think, phosphorus was also pretty prominent there. So this is now phosphorus. And I could undock that, undock that, maybe give it a little bit of a different color, because there's no coloring involved yet. Give that a bit of a different color. What's my... That's phosphorus, I guess, as a color. And then I can just go click on it, Control Copy. Click on the axis here, otherwise it will create a new axis, and Control V, and then we've got it copied in, paste it in, and yeah, so you've got your different proxygrams. So this is the sort of the quick way to do that. So if you missed the last session, the data set is the grain boundary simple one that Martin has sent out. Its run number is R04-11350. I've used that one quite a lot. Okay, so how do we generalize that to an n-dimensional analysis? But first, maybe applied for proximity histogram. And the way we do that is we voxelize our data. Yeah, we already had voxelization when we were talking about isosurfaces. Yeah? So if you have an isosurface is based on a voxelization of a data set in 3D. But this is now a one-dimensional voxelization. Yeah? And this is why we call it ND analysis, because you can actually use any dimension you want. Yeah? And let me just maybe visualize that. So, essentially what we're doing is we're creating histograms. So we're chopping up our data set into blocks. Yeah? And if we do a voxelization in 3D, what we're actually doing is, we have our data set here.
Peter, if you're drawn, we don't see your screen again.
Thank you, Martina. So if you're having a voxelization of a data set, what we're doing is essentially, we're chopping it up into a grid. Yeah, chopping it up into a grid, and then we'll look at each of those voxels. Yeah, voxel is pixel just for volume. Pixel stands for picture element. Yeah, pixel, picture element, voxel, volume element. So each volume element, each voxel that we have here, we can do some analysis with. Yeah, and that could be, calculating concentration, but it could be calculating charge state ratio. Could be calculating whatever the hell you want. I mean, you can come up with a bunch of things. And the dimensions that we have here, are x, y, and z. And of course, in Adam probe, it would be the other way around. We usually have z down, pointing downwards, but that doesn't matter for now. If we have a proximity histogram, if we have a proxygram, then a proxygram is a 1D voxelization. And here we just have natural coordinates, but here what we have is a distance coordinate. If we have a distance coordinate, so we have our, we have our interface, and now I'm just drawing a kind of weirdly curved grain boundary, or could be an isosurface or whatever. And what we do here is we need to create a distance variable. So we have our x, y, z, but this is not what we're doing here. What we're doing here is we're taking our surface normals, our surface normals n, which exist for each vertex or for each face, depending on which way you want to approach it. And they all have a length of 1, by the way. I'm just drawing them in different lengths. So for each surface normal, the length is unit. It's unit length. And what we're doing is we're actually looking up what the distance is between an atom. So say we have an atom here, an atom here, an atom here, an atom here. And we are calculating what the distance is to the vertices in this case. You could obviously say, okay, I want to know what the distance is exactly to the boundary, but that's a lot of computation to do. So we have established last time that neither Kamika nor we are doing that. So we are all calculating the distance to the distance along the normal, the distance along the normal to the closest vertex. The only subtlety that you have here is that essentially the distance that you're calculating, is the distance to essentially this plane here. So if you have a strongly curved surface, the distance deviation here matters. If your surface is not that curved, then it might not matter all that much. And then we are getting this distance variable. So we're getting this distance variable d here, and this is for our proxygram. It's a histogram of concentration versus this distance d. And the distance is 0, where our mesh is. The distance is 0 where our mesh is, and in our case, this is where our grain boundary is. This could obviously be an isosurface, and the distance would be 0 where the isosurface is. Or you could have a proximity histogram to a point object. Then the distance is 0 at the origin of the point. There probably won't be any negative values. So if you've got a point object, then you've got a point object. You might have a distance d to that point object. Distance d to that point object. Or if you have some kind of line object in 3D, then that distance would essentially be the distance to the line segment. Probably not the distance to the vertex, but the distance to the line segment. So just imagine you create a cylinder around it, and it would be the radius of whatever cylinder you have, and the distance to the line segment. And we're providing functions actually for all of that. So you can do lines, you can do, points is trivial, you don't need a function for that. It's just a Euclidean distance to the Euclidean distance to the point. Okay, so how do we do that? So let's jump back to MATLAB, and I didn't forget this time. We need to have a distance measure, and the distance measure is, let's call it distance, is pause distance to mesh, and you can have distance to mesh, distance to line, and distance along vector, because you might want to look up, for example, if you want to do a this diffusion along a dislocation, or something like that. Yeah, you want to see what the distance is along a vector, or along a series of lines. Yeah. But what we mostly use is distance to mesh or distance to line. And you see the absence that there is no distance to point function, because that's only one line of code, because it's just a Euclidean distance of the distance vectors. Yeah, so there is no separate function. I mean, it would be just a function with one line. So yeah, no function. So with distance to mesh, and yeah, so we need the pos variable, and we need the interface. That's FV4 in our case, and that's all we need. That's all we need. And off we go. And we've got the distance calculated. So now if we go into dist, our variable dist, you can see what the distance is. Oh, and we can see what the closest vertex is, which is pretty good, because it means we can go and say, okay, maybe we want to calculate stuff just for a particular vertex or for a group of vertices. And we're going to make use of that later. But for now, we're only going to care about the distance itself. So we can see, in this case, it's a very simple data set. Everything is happening in the z direction. So you can see, okay, everything gets closer to the grain boundary, and then eventually it becomes negative and goes to the other side of the grain boundary. So the question is now, how do we know what the surface normal is? Yeah? And how do we make sure that that's all consistent? Because, I mean, the surface normal per se, if I look into, if I look at at just this sketch here, there's nothing. What would keep me from actually drawing the surface normal into the other direction? Yeah. Because then, if the surface normal points into the other direction, then obviously this value would also swap. Yeah, we would look into the different direction, because the surface normal has a direction. And so how do we find the direction of the surface normal? And well, let's jump into Blender and just look into whether I can see the surface normal. Actually, you can visualize it in MATLAB as well, but usually I just do it in Blender. So in MATLAB, it's you need to calculate the surface normal and then just display it as a vector. I don't do it that often. In Blender, it's much easier. So where we have our grain boundary 2, and if I go into view, there is, I need to select the grain boundary. There is, oh great, they've moved that one. No, collections, annotations. Oh, sorry, we're in object mode. We need to move into edit mode. And if I'm in edit mode, we should be able...
Peter, one quick question.
Yeah.
Do we have right now our change grain boundary to export again to Blender?
What?
Because we have all just the old first model grain boundary in Blender and no grain boundary that we changed again in MATLAB.
I save that on the public into the folder where all the data is from that grain boundary. So Martin can email it out to everyone. It's a very small file, so that should work. That should work pretty quickly. For now, actually, you could use the old one as well. Bloody hell! Where did the... I should really spend more time with the new version of Blender. So where do we have? Where do we have these surface normals? Is there a new annotation? No, there's not a new annotation. No. Let me look that up. Display surface normals Blender 3.0. show normals. It's moved up to here, okay? So you click up to here and there should be, you can show the normals. You can either show the vertex normals or the face normals or split normals. And what we want is we want the vertex normals. And if you switch them on, you can see now, okay, we see the vertex normals. And they all point into the same direction. And actually, I could go and the vertex normals. By the way, the vertex normals are calculated because a vertex itself, a point, doesn't have a normal. But rather, what you calculate is you calculate the surface normal of each of the neighboring triangles, and the vertex then has the average normal of the neighboring triangles. And so let me just show let me just show the face normals. So you can see now you use the face normals and the vertex normals. And this is actually all the way it should be. And the question is now, how does it know which direction each triangle has its normal? And this is actually done very simply, implicitly, unfortunately. It's done implicitly by if you have a triangle, and the triangle has vertices 1, 2, and 3. Vertices 1, 2, and 3. Then the question is how to write it. I could write it 1, 2, 3, or I could write it 3, 2, 1. And essentially, you're just taking the cross product of that order, and then the surface normal either points this way or this way. And you can do that for each triangle. So it's the order of the vertices, the way we write them down, that gives us the direction of the surface normal. Of course, you can think now, what happens if I'm very inconsistent and I have flipped triangles? Well, what you can do is you can go at mesh, and there should be a cleanup. Generate, dissolve, fill holes now. Thank you. Maybe I do not remember. So there should be a function mesh. So we should obviously select everything. And there should be UV. No. Where the hell has that been moved? We're going to find it. Normals. Normals, you can either flip the normals, then all the normals will point into the other direction. So maybe you want to analyze, you want to make the positive z-axis or the negative, the positive z-axis, the positive direction, which we don't. We now go from the top, from the bottom of the data set from 0 up, but maybe you want to go in the other direction. Now we would have flipped them all. Or you can go recalculate inside and recalculate outside. Obviously, in this case, there is no inside and outside because it's an open mesh. But you can recalculate inside and outside, so that if you have some flipped triangles, it will just go, okay, most of the triangles, most of the normals point this direction. Maybe I need to jump, maybe I need to move the other ones to point in the same direction. Okay, so this is something you need to keep in mind, because if you have inconsistent normals, then sometimes you're sort of analyzing in one direction and then you're analyzing in the other direction somewhere else, and that is something you always need to keep in mind. So if you have isosurfaces, then the isosurface algorithm makes sure that all of the normals point in the same direction. And the definition, by the way, in the original paper about the isosurfaces, it's a very, very famous paper, Lawrence and Klein paper. The surface normals point into the direction of higher value, I believe, or lower value, one of the two. Doesn't matter for us. Yeah, it just needs to be consistent. And sometimes, you might want to go and flip the normals of your isosurface for some reason, because what is inside and outside might be a different definition that you have, and then you can go into Blender and do that. Yeah? But that's a very important thing for us. We need to know which way they, especially if we hand model the grain boundary, hand modeled anything, you might want to check if all of your normals are consistent. And if they're not consistent, you go to Mesh, normals, and then recalculate inside, recalculate outside, or flip them all if you want them to point into a different direction. Yeah. And which direction where? Okay, so this was the original direction we had. This is just something you really need to take into consideration. Okay, so now we've got the distance calculation, and I can see I will just copy that into the. I'll just copy that here into here. And now we can actually calculate a concentration profile based on that distance. And quite honestly, it doesn't matter what, for the calculation of a concentration profile, it doesn't actually matter if it's where the distance comes from. Yeah, we could just take the Z direction. We could just take the X direction. We could take the mass to charge ratio, and it doesn't make any sense, but you could take anything you want, anything you want as a distance. A distance that would actually make sense is, for example, to use the evaporation sequence as a distance coordinate. That actually makes sense, because sometimes you want to know how something evolved during a measurement. Yeah, so you can use that as a distance coordinate. And for that, what we need to calculate first is, if we want to chop up our data set based on distance, then we need to know what the bounds are for each block that we're using. And we have a function for that, which is which is called bin vectors from distance. So you get your bin vectors because you have more than one bin, because you might have more than one bin dimension. In this case, we only have one bin dimension. And our bin dimension in this case, we're binning just in one dimension, and this dimension is dist, or distance. You could make a voxelization based on the distance to the object and two other things. Yeah, so that's why we call it n-dimensional binning. And those bin vectors, by the way, they're independent of the number of they're independent of the number of dimensions you have. So you can have 1, 2, 3, 4, 5, 6, 7, 8, however many dimensions you want to chop up your data set with. Yeah. In this case, it's just one dimension. Yeah, and we're going to in this dimension chop at a value of 0.5. In this case, it's nanometers. Yeah, it might be counts if it's it might be counts if it's it might be counts if it's if you go by evaporation sequence, or it might be you might use charge state ratio, and the charge state rate what else can you use? You can use a charge state. In the charge state, then it wouldn't make sense to bin by 0.5, because charge states are discrete. So you would bin by 1, yeah, because you would then bin by whatever charge state you have, for example, and create some analysis on that basis. Yeah, in this case, it's just dist, just one variable, which is a distance to our object, and we are using 0.5 as the distance variable, as the distance bin, and we're binning by this constant distance. Now we're binning by constant distance. Oh, sorry. Dist dot distance. Dist is the variable that contains the distance, and we want to bin by dist dot distance. And if we now look, we've got bin centers and bin edges, and they only have one entry with one vector that tells us, okay, we have bin, in this case, bin centers at 0, 0.5, minus 0.5, and we have bin edges, which are just shifted by by 0.25 of a nanometer. So where do we have the one that's closest to 0? So we have got bin edges. So one bin goes from minus 0.25 to plus 0.25, and we have the bin centers at 25. That's at 0. So we give you bin centers and bin edges. And right now, what we've done is we have. Let me just close some of those variables. Otherwise, this gets a bit overloaded. And now we've right now bin bin vectors a b bin vectors from distance. Bin vectors from distance. You have two modes. We have two modes. We have one mode that is distance. So you tell it at which distance it should chop the data set. And the other mode is count. And count works for 1D. So if you want to make a proximity histogram, for example, where you make sure that each bin that you have has the same number of counts in it, just imagine you're having a highly curved surface, or you have something that's close to a dataset edge or whatever, and especially if you look at precipitates, they are highly curved, and sometimes you have the issue that the data becomes very noisy when you get to the inside of the precipitate, just because the amount of, if you go by distance, the number of atoms that you have in your last few distance bins is just extremely small, so you get a lot of statistical noise in it. So the option that we've put in is that you don't go by distance explicitly, by nanometers, but you go by count. So you say, okay, I want to have each bin to contain 10,000 atoms, 50,000 atoms, 100,000 atoms. So you explicitly can tell it how many atoms you want to be in per bin. Obviously, there needs to be some rounding, so you don't get the exact number, but you get either plus minus 1 atom, essentially. And you get the same. You get the distance vectors, but of course, in this case, they're not going to be equally spaced. They're not going to be equally spaced in distance. Okay, and the next thing we're going to do is we're going to create. In this case, I call it voxel, even though it isn't voxels. It's actually just one-dimensional, but I just got into the habit of calling those voxels because they represent volume elements of some weird shape, or shape one or another. And we're going to do that with pos, and we're going to do that with along the variable dist.distance. You can lose the braces. They're not really necessary because we're only one-dimensional. And the limits by which it's going to be chopped up is our bin edges. And if I execute that, what you can see is I get a variable where each variable, where each a cell array, where each cell is a pos file. each cell is a POS file. And obviously the center of each POS file along the distance variable is given by bin centers. It's given by bin centers. So if I go into that POS variable number 9 which has, I don't know, about 20,000 entries, then this variable number 9 is minus 8 nanometers away from our interface. In this case here, obviously, unless we go to the boundary of the data set, most of the bins are going to have relatively similar numbers of atom entries. But you can see that once you go, the first one only has 3 entries. There's 3 atoms in there. So calculating a concentration from 3 atoms, I don't know if that makes too much sense. I mean, you can do it, but you can do it by hand. It's 2/3 nickel, 1/3 iron. Done. Okay. So we have done that, but we could do it in 3D. So I could go and calculate a 3D voxelization as well, and just go and say, okay, I want our voxelization basis to be pos.x, or maybe I want to do it in detector space. Pos.detector_x, pos.detector_y, and I don't know, pos.ion index probably, ion index, something like that. And then I need to provide 3 numbers here. Maybe I want to have 5 millimeters in detector space, and then in Z every, I don't know, 20,000 counts or something like that. So you can do any dimensionality you want. Obviously, I'm not going to do that now because we do proxigrams. But you can do voxelizations in detector space. You can do whatever the hell you want. Go do that freely, as you like. Okay, so we've got our voxelization. So the next thing we need to do is we need to have some way to calculate the concentration in there. Some way to calculate the concentration. And let me just give the last couple of commands to you in the chat. So how do we calculate the concentration? And for the concentration, we need something called a concentration kernel. So what the concentration kernel is a function that calculates the concentration of something in a voxel. You can now go and calculate any property you want for the voxel. For example, I don't know, count equals, what do we do? Self_fun. So self_fun is the function, is applying a function to each bit of a cell. And the function, okay, maybe I should explain what function handles are in MATLAB. Because this is maybe a little bit of an advanced topic. Function handle. So you can have a function. You can assign a function a variable. So you can, for example, here you can have the function y equals compute square of x. And then you can say f is at compute square, which means then that this function, this variable f, then represents the function compute square. In this case, it's a very simple function, just computes a square. Obviously, that's not a particularly helpful function because it's just one line. But in our case, the function we are talking about is a function that calculates a concentration. But we can have any kind of function we want. And the function we are providing you for concentration for now is calculate concentration simple, which is just taking the allocations, the ion allocations we did with the ranging, and then apply that function. But you can use any function you want. And one thing I would really like to do in the near future, I've been talking about that for a year now, is, for example, take the deconvolution function that Andy London has in his Atom Probe Lab suite, yeah, where you can do deconvolution. Yeah? So if you have mass spectrum overlaps, yeah, you could take that concentration function, chuck it into the analysis here, and then have everything deconvoluted. Yeah? And I think this would be very, very, very helpful for a lot of Atom Probe projects. Yeah, but for now, we're just going to create an anonymous function, yeah, where we calculate the concentration of our pos variable. Let's just open the function so that you can see what it does. Pos calculate concentration simple. Oh, I've started the deconvolution one. It's not working yet. Don't use that one. Yeah, doesn't fully exist yet. But this function, what you provide is the pos file that you have, the detector efficiency. Yeah. The detector efficiency in this case we're providing because we're getting some statistics out. Yeah. So we're getting out a concentration table. But okay, maybe we'll just do the concentration calculation for the entire data set so I can show it to you. And then we have an exclude list. So there's some elements we usually want to exclude. For example, we want to exclude the unranged elements very often. Otherwise, they would be part of the whole thing. Yeah? So we would say, okay, this many atoms are unranged. And you can provide a volume name. So if you do a lot of concentration calculations, say you have 15 subvolumes in your data set, you might want to provide a name for each volume so that they can remember which one's which. And that name is also used. We have some plotting functions for concentrations, and that name is then also used in the plotting functions. So you can compare 5 different volumes or 5 different data sets, yeah, and chuck everything into one plot, and the plot will automatically pop up with the right name everywhere. That's not as important for us right now. What is important is that we have a pos variable and we have an exclude list. So what is in our exclude list? Unranged. Yeah, what else? Maybe we want to exclude hydrogen because it's not actually contributing. We know it's from the atom probe analysis, so we might throw out hydrogen as well. Yeah. And now we've created that anonymous function, that function handle, which represents the function pos concentrate calculate simple at a detector efficiency of 0.37, which for this data set is actually not correct. It's 0.55. Yeah. And we have excluded hydrogen and we've excluded everything unranged from our calculation. Let me just do that for the. Let me just do the calculation. Let me just concentration is pos calculate concentration simple 0.55 unranged and hydrogen. Oops. Hydrogen. And what we will get is a is a table that just shows us, okay, what for this volume that we've called cons for some reason. Yeah, but I could call it, I don't know, let's call it something different. Let's call it Hansi. And if I now look, okay, the volume Hansi, has a distance assigned to it of 0, because we don't have any distance variable assigned to that. I mean, it's the whole thing, so distance doesn't make any sense. It's calculated on an atomic basis. It knows that based on whether you did a decomposition, where you assigned ions or whether you assigned atoms. If you assigned atoms to your pos variable, and we'll do atomic, and it will show you what the count is of each atomic species, what the concentration is, not in percent, but in actual concentration, and we'll show you what the variance is. And this is very often what we use for error plotting. I personally don't like that very much because the statistical variance is not actually the measurement error. But yeah, this is what most people use for error plotting. And we are now going to apply that to all of our individual concentrations, and I will just copy the last few bits into the chat again. And we're now going to apply that to our proximity histogram. So we're going to go concentration is bin apply concentration kernel. So we are now applying this concentration kernel, this kernel function, to all of our different volumes. So we're going to apply it to the variable vox. We are going to assign the bin centers as the distance. Then the function we're using is this function ck up here. And by the way, everything that you pass, so here you can see this @ sign. So any of the things behind that @ sign, they are the variables that we are passing to this function when we execute it. If we put 0.55 here, then we have said, okay, when we invoke this function through this function handle, it's always this 0.55. So we don't need to repeat the 0.55. We don't need to repeat the unranged, and we don't need to repeat the volume name if we've assigned any, but we haven't assigned one for a voxel. But you could do that. Okay, and in this case, we'll just calculate that, and now you can see we have a concentration variable that's a list of all of the different concentrations, counts, concentrations, and variances for all the different voxels. You can imagine if you do that in 3D, you have a lot of, a full voxelization of the data set, not just a proximity histogram or a concentration profile. This can become a pretty long list, but you can find anything you want. So you can find anything you want, and now we have all of our individual things allocated, and there's actually one at 18.5 that doesn't really contain anything meaningful. So all of the concentrations and variances are not a number, but anywhere in between, we get a good measurement of concentration. Of course, you could write kernel functions to do whatever you want. Charge state ratio is actually a pretty good one. Stuff like that. You can do that in 2D. You can do that in 2D. You can do that in 3D. So you might want to have a charge state ratio field desorption map, or you might want to have I don't know. You can come up with all kinds of crazy stuff. There's always cool stuff that you can do with Atom Probe. The next thing we want to do is we want to plot that, and we have functions. One of the cool things is that now here we have distance allocated. So we have distance allocated, and we have a lot of information here. So we might actually want to plot that. And we have a convenience plotting function for one-dimensional stuff. And that convenience plotting function is, remind me what that is. Something with concentration profile plot. Concentration profile plot. And for the concentration profile plot, we need to actually look at what we want to plot. So we need to select from the concentration list that we have what we want to plot, because you could plot variance, you could plot count, you could plot anything you like. Well, these are the three things we have. So any of those three things you could plot. And then again, you have some exclude list here as well. Just to show you what that what this first thing here does is, if I go and just select this bit here, I'll just create a variable called test or demo or whatever, because that's not actually something we need. And in this variable test, we've just select that the concentration format we want to look at is concentration. And if I now open this test variable, you can see it goes -12, and it's only showing the concentration. And this is actually what we want to plot. I could go count. And if I open the variable now I've got all the atomic counts in here. And we could plot that. There's merit to that. Okay, so we go back to concentration profile plot. And there, in this case, I want to exclude the hydrogen again. We've excluded in the calculation already, so in this case it wouldn't be necessary to exclude hydrogen because we don't have it in there anyway. And I want to use a certain color scheme, which is always cool. Build a cool color scheme for your project, and then you can use it very consistently. And this then gives me a plot of all of the different elements I have in there. So now we have a proxygram of all of the elements in there, and which ones are enriched and which ones are not enriched. And this is already pretty nice because I can go and just export that as an image or export that as a vector graphic. And this is the really brilliant thing about MATLAB is you can export your figures as vector graphics. So you can go and put that into Adobe Illustrator, Inkscape, CorelDRAW, and everything remains editable. So you can edit colors, you can edit I don't know, line styles and whatnot. And that's the really cool stuff about it. And it already says, okay, distance, atomic concentration, and all of that stuff. We can actually exclude more than that. So probably we want to exclude nickel. You can go and manually delete some of the elements later as well. So in this case, we've gotten rid of nickel, for example, because nickel is the main element. But of course, you can go in here and you can select, maybe what have I selected now? I can't tell from the color right now, but I can go and delete those, and so on and so forth. So you can plot all of them and just delete the ones that are not interesting. I don't know if this is interesting. This is carbon in this case. This is, what is this? I don't know, niobium. Can get rid of niobium. It's maybe not that interesting. Doesn't do anything. We can get rid of titanium. Doesn't do anything. And then, the interesting bits then remain. We've got a dip in aluminium. I don't know if that's interesting or not. Maybe it is interesting. Maybe it isn't. But anyway, so you get the full freedom to do any kind of analysis you want. Okay, let me just copy all of that stuff into again, flexibility and scriptability. That's the important bit. So if you have a certain type analysis that you want to do, I think you could see that a lot of that, the interface creation in this case for grain boundaries, that we won't get around having some manual interaction there. But apart from that, then the rest, once you've done that once, you can just go and take all of the commands, copy them into a script. Live scripts are very, very good for that because they give you the documentation visualization. You can just go and export everything as a PDF afterwards. And if you want to do that for 100 samples, 1,000 samples, it's not more work for you than it is to do that for one sample, for one data set. And that's really the power here. Okay, so this was a proxygram, and now we want to move on to ND analysis. So we might want to go and do a voxelization based on that. Because in this case, we can apply any function we want. We can apply any function we want in 3D to our voxelization. So you can do a charge state ratio voxelization. You can do a voxelization where you need to have some collective information about the atoms in the voxel, not just counting what atom it is, but calculating some statistics, calculating whatever information you want. And to that end, we're actually going to abandon this small data set because voxelizations in this tiny data set are not that interesting. And we're going to take the data set that I used yesterday, where we created the isosurface, and create an iso concentration surface in this data set. And so I'm going to clear out all of the stuff that we have here. By the way, if you go like, oh no, don't delete everything, there's so much information in there, you can go and save the entire workspace, or save particular variables. So you can go and and save the entire workspace. And then you can just continue the analysis based on all of the stuff you had in the workspace at that time. Or you can just save individual things that you've done stuff with. For example, maybe you want to save the concentration list, and you can go save as and just save the concentration list and save them as .mat files, and then load them back in, do stuff with them. And MATLAB is actually very good in compressing data. So if you think,
Peter,
yep.
Just quick thing. I would not recommend to save the entire workspace, especially if you have a really big data set. I would recommend to save just the variables that are important for you, like the concentration calculation. And the next time, if you continue working on your data set, just open the mass spectra figure and load the POS file in again, and just redo the POS allocate to range function, because it's way easier in working with the MATLAB toolbox than just saving the entire workspace, because if you have a big data set, it can take a lot of time to save.
Yes, and you would have another copy of your data set floating around that you might not need. Because, I said 4 terabytes is a lot of storage, but, if you can still use up 4 terabytes if you want to. So maybe save everything apart from the POS variable or apart from some of the big variables that you don't need. Because sometimes if I work with a lot of subvolumes, multiple data sets, you might literally have a couple of gigabytes of stuff in your workspace, and then it's maybe really not efficient to save everything. So thanks for the hint, but that always depends on what you're doing at the time. But I'm just gonna throw everything out that we had so far, and we're gonna start from scratch again. So just clear. Everything's gone now, and I'm just going to load in the data set that I worked with yesterday, which was the one data for Isosurface, I think. Which one was the one for interfacial access? Oh, that was the one from Martin, right? Yeah, but we'll use the one for Isosurface so that I can show you how to calculate an Isosurface that way. Okay, so let's load in the POS file. Not simple grain boundary, but data for Isosurface, and it's an EPOS. We can load that in. Take a second or two, and yeah, there we go. And then I might reuse the code to load in the mass spectrum. And now we have the mass spectrum reference loaded in, and we can start working with our data and just allocate the ranges. Pause allocate range, and we are going to work with elements again. So we can choose to work with elements, or we can choose to work with ions. Very often at the end, for papers, we choose to work with elements. Because we hopefully have put in a lot of work to correctly identify them, to identify the individual ions. But of course, all of the analysis is also possible based on the ions. And again, if I look into the POS table, I have X, Y, Z, mass to charge, fight time, voltages that we're not needing now because we're not doing the reconstruction. And we can see for each entry what ion it came from and what atom we allocated it to. And we can see what isotope it is. So you can do proxigrams for isotopes. No problem at all. The information's all there. You can look. You can do displays of if the ion complexity was locally higher, if there were multi-hits, whatever the hell you want. Yeah, there's a lot of different things you can do. Okay, and in this case, the voxelization might take a second or two, because the first thing we're going to do is we're going to calculate the bin vectors. And in this case, we're going to voxelize. This is a large data set. Out of 56, so we're going to do isotropic 5 nanometer voxels. You don't need to have isotropic voxels. Yeah, you can have voxels that are anisotropic if you have some reason to do that. And sometimes, maybe you want to do field evaporation, map stacks, stuff like that. Then you have very anisotropic voxels. Okay, and you want to do that by distance, of course, because we're three-dimensional, and it doesn't make much sense to go by count in 3 dimensions, because otherwise the voxels wouldn't fit together. That really only works in 1 dimension. Okay, so we've got the bin centers and the bin edges, and now we are calculating the voxelization. In this case in 3 dimensions. That creates a lot of sub-pos variables. I think it might be 10,000 variables, something like that. Well, we can look that up later on. So it might take a second or two. By the way, that was fairly quick. We also have a function of, I think, what is it called, pos to voxel, which just essentially takes out individual elements. It's called pos to voxel. Voxelize or voxels or okay, so we in the Isosurface workflow, we use the faster function, bin vectors from distance, pos to voxel, because we used pos to voxel, and there we voxelize just a particular species. And this is a very fast way to do that. In this case here, we're choosing the slower way to do that, because we want to have the ability to do advanced analysis per voxel. If you do a regular concentration calculation, just concentration or count, then this obviously does the same thing, because you voxelize all of the atoms compared to just a particular species, and that's a good concentration calculation. The downside of this is, of course, is sometimes you would just want to go with the ranged atoms or whatever. And now what we have is a variable where you can see, okay, sometimes we have entries, and you can see in the voxels that are relatively full. How many atoms do we have in the larger voxels? We have about 2,000 to 5,000. In the fully filled voxels, we have about 4,000 or 5,000 atoms in each voxel. In each of those 5 nanometer voxels. And I guess, depending on what the concentration is, that, might make sense. If you've got ppm level stuff, maybe not. If you've got percent level stuff, that probably works out pretty okay. In this case, we'll start and have our concentration calculation kernel again. Create that one again, and then apply that voxel to our voxel. Apply that concentration kernel to our voxel at the bin centers. And now it's going around and calculating 17 by 17 by 50 concentrations. And that will take a second or two, which gives me the opportunity to ask, so how many of you are Were most of you able to follow? Okay, that's good. That's good. There's at least some green. Okay, and now we have a concentration variable that's the same size as our voxel, volume. So we can actually now pull out the information directly from those individual concentration variables. You can see they're all the same size because they're all containing the same information. And I will just pull one out randomly. Is concentration. And these are cell arrays, so you should know the curly braces, what they do. So let's take one in the middle. So I don't know, 8, 8, 25. Yeah. Oops. 8, 8. Oh, sorry, the second brace was not a curly one. And if I go now, I can look into that individual concentration element. And yeah, in this case, I don't think I've excluded. Okay, so we've ranged helium again. Okay, that was not a good idea. If there was hydrogen, it would say, okay, if I got a count of this many hydrogen atoms, but the concentration is 0, because I told you make it 0. Yeah. Okay, but we get a concentration measurement, and basis of that is about 2,000 nickel atoms, 1,500 chromium atoms, and we get the variance as well. And the variance is still pretty low in this case, because it's the statistics are pretty okay. If I go into a voxel with very few atoms, then the variance statistics are probably not all that great. And of course, with voxelizations, if you shrink your voxels to very, very small voxels, maybe 1 nanometer voxels, your variance might become pretty bad. Yeah, your statistical variance. Okay, now the question is, I've got this great variable with all of these different concentrations in it, and maybe even I've found a concentration kernel that does deconvolution. Yes, I can do deconvolution and stuff like that. So how do I pull out the aluminium concentration, for example? And that's actually done with a built-in MATLAB function. Yeah, that's called selfun. Yeah, and selfun is just applying a function, just like the concentration kernel that we had earlier, applying that to each entry in a cell array. Yeah? And each entry in our cell array is a concentration. And in this case, what we want is, if we go back into our test variable here, we want in this variable we want the second entry, which is the concentration. We could write it in a little bit of a different way as well, so that it's maybe a little bit more readable. I've just shorted that out. We could call that x dot format equals concentration. X dot format equals concentration. And and the variable we want to do that with is our cons. So now if we look at aluminium concentration, we just have a nice variable that shows us what the aluminium concentration is locally. And let me just put that in to the chat. And again, in this case, it doesn't matter how you chopped up your data set. Yeah, you could chop it up by any means. You could have distance counts, whatever. I'm pretty sure you people are creative out there. And I can actually look at that in 3D. So MATLAB has a volume viewer. I've showed that thing to you yesterday already. Volume viewer. I have to find out what the other volume viewer thingy actually does. That would be pretty interesting. Import volume from workspace, and the one we want to import is aluminium concentration, because this is a 3D volume, and you can see the distribution. We can maybe adjust the filter a little bit, and you can see where your precipitates are. But maybe 5 nanometers was a little bit coarse. Maybe we want to have it a little bit finer. Maybe we'll rerun the voxelization with half the voxel size. The problem with that, of course, is we're in 3 dimensions, so half the voxel size means 8 times the voxels. So we are order of magnitude more voxels in the end. But let's do that, otherwise our outline is maybe not all that great. Or maybe we go 3 nanometers. So let's just rerun all of all of the stuff that's relevant for that. So we'll choose the bin vectors from distance, the voxelization. We already have the concentration kernel, but we can rerun it. Why not?
Peter, for the concentration kernel, maybe you choose that other detector efficiency.
Thank you, Martina. Thank you, Martina. That's actually a very good hint. Yeah. So we'll take all of that and couple out the aluminium concentration. You can just move that up here. And we'll do 3 by 3 by 3 nanometers, and then this is all fine, and we have 0.37 detector efficiency, and that's all there is to it, and we'll let it run. So I think I hope you understand the power of being able to script all of that analysis. And I'm very happy that Kamika actually added scripting in the AP suite. Unfortunately, we don't have AP suite, we have IVAS, but scripting for the win. Especially compared with the MATLAB live script or Jupyter notebooks, where you can integrate all the visualization and then just let it run for however many data sets you have. And I think one thing that is really, really important we don't have right now that we need to develop in the next time is actually a deconvolution kernel. So that if you have mass spectrum overlaps, that on a statistical basis you can still pull that apart. And if you do that as a concentration function like here, concentration kernel, deconvolution kernel, you can just plug it into proxigrams, you can plug it into voxelizations, you can plug it into analysis of subvolumes, and so on and so forth. And this is why we want to keep everything that flexible, because maybe for your application, it's relatively easy to write something like that. If you work on superalloys, you might have an overlap between chromium and iron, an overlap between nickel and nickel and iron. And you're just going to be able to say, okay, chop up anything that's in this range, chop it up to allocate it this percentage to iron, this percentage to nickel, and stuff like that. So writing deconvolution kernels for a specific application isn't actually that hard. Just writing it for everything is hard, but for a specific application, it's not that hard. So you can come up with your own concentration function, chuck it into our analysis here, and off you go. Bob's your uncle. So you can see, the larger, the smaller the voxels are, the slower it will be, obviously. So we now have 10 times as many voxels as we had before. I mean, 8 times, but now we went with 3, so maybe 5, 6, 7 times more. But that grows pretty rapidly. And this is why we still offer the direct voxelization option as well, which with the function, with the Isosurface workflow that I've shown you earlier, because that one is relatively quick, because it just counts, it just goes in and counts how many atoms of a certain type you have in a voxel, and that goes very quick. But in this case, we actually create a variable, essentially a pos variable for each subvolume. which means you can do any analysis you do with an entire data set just on that subvolume, but it also means that it takes a little while to generate them if you create a lot of them. But we still have a couple more minutes to get to the isosurface. I'm pretty sure it's going to be finished until then. Yep, all done. I should have probably also added some time measurement to that. Yeah? And you can see now we have a voxelization that's 28 by times 27 times 82. Yeah, so that's a lot more. So it's we have. So that's what about 61,000 subvolumes that we have created. So again, sometimes we need that, sometimes we don't need that. And so the next thing we want is we want to have an isosurface from that. We showed you yesterday already the quick way to calculate isosurfaces. We also have the isosurface widget, because that allows you to really drag, to just drag a slider and set certain things. But one thing that's very helpful is also always to plot a histogram. Apply the histogram of the concentration. In this case, it's our aluminium concentration. Our aluminium concentration. And that should give us an idea of where we could have a reasonable cutoff. And now I've plotted that somewhere in an existing figure, which is a stupid idea. So probably now our master charge, I should close that. Probably now our mass spectrum contains a plot. So don't do that. Maybe close it beforehand. Let's just reopen that. Create a new histogram from that concentration. And we can see here that well, we looked at that yesterday already, so probably about 7% is a good cutoff. But I think nickel plus aluminium was a better cutoff yesterday. Anyway, doesn't matter all that much. The next thing is we calculate an isosurface, and that is a built-in MATLAB function. So this is not something we provide, it's a built-in MATLAB function. And we create an isosurface, calculate an isosurface, and there's one subtlety here. And that for some reason, X and Y are swapped in MATLAB here in the isosurface function. So you need to take care that bin centers 2 and 1 are swapped. Don't ask me why, but that's the way it is. And we calculate the isosurface for 7%, I believe. Oh, not. Of course, we want to calculate it for aluminium concentration. And I think I might have filled the memory up of this PC pretty well. I have to check how large the memory on this PC is, because the isosurface calculation should actually go in a fraction of a second. It should go very fast. And I can just go and display the isosurface. Display the isosurface. APTify our axis. So we've got a nice looking axis. Oh, no. Sorry. I'm still not used to that. That's now called something else. Axis spatial APTify. And there we go. We have our isosurface. Of course, our isosurface doesn't know, our isosurface doesn't know that it has individual objects. And usually, or very often, we want to do an isosurface to one particular interface here. So, and we can do that very easily. We've got a function called split FV. Or I think it might be called a little bit different in the toolbox now, right? Patch, probably something patch split connected areas. patch split connected areas. No, not patch split connected areas. And here there isn't actually anything you have to provide, because all it does is it looks up which individual patches, which individual objects are actually connected. And then we get a variable fvs that is an entire list of individual isosurface objects. In this case, 153 objects, and you can plot each individual of them. And some of those are just initial, are just some, you can see just very small triangles. So just one individual triangle just dangling off somewhere. And what we might need to do, and they're mostly occurring at the boundary, but there are a lot of statistical fluctuations of the concentration, and we might want to get rid of those. And that is actually fairly simple. Now we have another function which is called patch filter by size. So we just go fvs is patch filter size. And we put that list into here. And we say, okay, how many vertices at least does our object need to contain for us to not drop it? And I'll just set it to 50. If that's a good idea or not, I don't know. Or maybe 100. Maybe 100. Scalar structure. Do we have the splitting in there? We do have the splitting in there, obviously. Sorry, my bad. So now we filtered all of the small patches out. Sorry, I should have done that before I split it. And so we can do the FV split connected areas. And if I now split it, okay, obviously there wasn't any. Let's go to 10 so that we have more than one that's left over then. What did I already? Let's just recalculate the isosurface. I might have dropped stuff in the in between. So let's recalculate the isosurface. Then filter the size, filter by size. Again, sometimes I don't remember what the individual algorithms do, but you can just go click on them or type help, and then it will show you in detail what the individual algorithm does. I think we've done a pretty okay job at documenting everything. Okay, then we go. Well, let's just plot that one. Let's just plot that one now. And since I've still got the old one open, I'll just reopen a new window and go. Why did MATLAB slow down? What is MATLAB still doing? Shouldn't be doing anything. So we can rotate in 3D, and now you see all those small triangle bits are gone. and we're only left with the larger objects that are actually interesting for us. And so I can go FVs is patch split connected areas. And now we should get a larger number of them. So now we have 25 that are left. And I'm just going, and you know, very often I just plot them in different colors. So I could go, let me just open the other figure. I just go for P equals 1 to length of FVs. Yeah, or I could just say, and then go plot handle P, so that we can programmatically access them later on, equals equals that. Probably it would be good to have a different color for each individual patch, but I'm not going to do that right now. And then end. And then you'll have the same thing as before. You have the same thing, the same plot as before, but this time it's all individual objects. It's all individual objects. It's all individual objects, and if I go and choose a selection tool, I can select individual. Objects in there. Now I can select individual isosurfaces for analysis, and that's what we're gonna use later on. And I don't know why MATLAB just got so slow. It might just have to do something with Java. So later on I might restart it. So the last action we're going to do is actually export those patches to Blender. So just because we're going to use that later for some funky analysis. And we can do that again with patch to OBJ. And in this case, we're going to export our FVs. Oh, sorry. I just plotted these. That was stupid of me. I just plotted the same one 25 times over. I was stupid. Yeah. It's because FVs is the one that we have, and where we have everything split up. And let me go and go into data for Isosurface, and then I will call it aluminium 7% Isosurface. You could actually put some information about that also in the OBJ file. The option is given in the export function. And let me open Blender, and I'll just open a new Blender file. Open general, and we'll just discard that one. Usually, you know, if you do analysis, I would save this as an analysis file, but we've saved everything externally, so I'm not going to do that right now. So just a new file, delete all of the default stuff in there, file, import wavefront OBJ, and again, Y forward Z up. And we're going to data for Isosurface, 7% Isosurface. That's all fine. And we have all of our individual meshes in here. And just like before, you can work with all of those meshes. So in this case, we've got 25 of them because we had 25 isosurfaces. And we can go and work with those meshes. We can edit them. We can make them prettier. For example, we have some weird pinch point in here, because later on I will explain to you what the topological problem is that we have with with isosurfaces. Sometimes in analysis, and I can delete some. I can do whatever funky thing I want with our isosurfaces in here. Or for example, if I've got a nice and closed up surface, I could, for example, go and export that or go and 3D print that. Yeah, and that's I think something that's always very cool if you've got cool data to go and hold it in your hand. Okay, and with that we'll close this last bit of the session, and I will just throw all of the stuff that I haven't put in into the chat. I will put into the chat. Even the stuff that was dumb. Okay. Good. So we now know how to create analysis objects, interfaces. We haven't worked with line objects. We haven't worked with point objects. But a lot of you are probably interested in some kind of interface. And these are planar objects. And we now know how to create planar objects in some more sophisticated ways, in some less sophisticated ways. And by the way, some of the stuff I was talking about with remeshing and everything, this also works with isosurfaces. So I can open instant meshes, and I can load an isosurface into instant meshes as well, which is something that sometimes is actually pretty reasonable to do, especially later on when we move to interfacial axis mapping and concentration mapping and stuff like that. Then it can actually be pretty important that we make a nice mesh out of our isosurface as well. So test data out of isosurface, aluminium 7% isosurface. I don't know what the problem is. Some of you can try to load the isosurface into instant meshes and make it a pretty mesh. Okay. Any questions about the ND analysis object creation and ND analysis generally? So essentially, it's 1D concentration plots, 2D concentration plots, voxelization, proxigrams, all thrown into one concept, because really they're all the same concept. You're voxelating based on some dimension, on some distance equivalent, on some distance function, which could be all kinds of things. It could be hit multiplicity, it could be charge state, it could be X and Y, reconstructed X and Y versus hit index. It could be anything you can come up with that represents a generalized distance can be used for all of the analysis. If it makes sense or not, I don't know. It depends on what you want to do. Okay, so I'll stop the recording then for now and upload the recording, and then we'll see each other again in about an hour. I'm going to stay in for a couple more minutes if you've got some more questions.